So it's my utmost pleasure to have Ben Reed as the opening speaker for the research colloquium in fall. Ben is at San Jose State University. He's an assistant professor over there, and he started a couple of years ago teaching networking, operating systems, and distributed systems. And he has had a fantastic stint at many of the, or I would say all of the prominent Bay Area companies. He was at Facebook, building distributed systems, at a startup, at Yahoo Research, at IBM Almaden, and he did his PhD from UC Santa Cruz. Ben is, the most interesting part is that Ben is a DePaul alum, and
That's right.
for us, that's the most interesting part. And he finished his graduate studies a long time ago, I think somewhere around 93, if
yeah, it was a long time ago.
Long time ago.
Yeah.
And Ben and I think we met at NSF workshop, and it was like we just started chatting. It's so interesting to talk to him. He's built the Apache Zookeeper, which is what I believe he'll be talking about.
Right.
It's the coordination mechanism underlying Hadoop, and it's one of the widely used systems. So without further ado, I'll let Ben take over and tell us what he's been up to.
Great. Well, thank you. And thanks for the invitation. It's really cool to be back at DePaul. I kind of wish I could go back to DePaul. I really love Chicago. It's a great city.
Yeah, we should have you sometime. Yeah.
It would be awesome. Although the weather, I got to tell you, I didn't realize how bad the weather was until I moved here. So, but yeah, it's really great. I really loved my experience at DePaul. It was really pretty awesome. Yeah, so I have a long background in industry. I had this idea after I graduated that I would kind of go into industry to get grounded a little bit before I came to academia, and I really loved it. It was really fun. So I ended up staying much longer than I expected. So I tend to have a very like engineer view on a lot of these things. I guess the interesting thing too is a lot of the distributed systems I actually learned from colleagues in research. I came from a storage background. So I learned a lot from my colleagues. And I also like to have very interactive talks and discussions, which I realize is a little bit hard with Zoom. So, but please, if you have questions or comments, please feel free to jump in, because I do like that. All right, so just to get started, I always, actually, whenever I teach classes, I always wonder what people think when they come to your class, so like what they think they're gonna learn. So I'm wondering, when you hear the term distributed systems, what do you think about? What is a distributed system to you? There's no right
Runs on multiple machines.
Okay, multiple machines. Yeah, I think that's an important aspect, is there's multiple machines involved. Any other ideas?
Well, there's a network, no shared state.
Oh, good. Network. Yeah, the lack of shared state kind of separates it from, parallel processing. Yeah, good. Any other ideas? Okay.
Each node is independent.
Independent? Yeah, the machines are running independently. Those are all really great, great aspects of distributed systems. There's one definition that I love, just because it's what we all experience. There's a researcher, Leslie Lamport, who does a lot of the foundational work in distributed systems. And he said a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable, right? And this, I think, really captures what a distributed system is, right? There's a whole bunch of machines involved. There's networking, communication, but there's also dependencies. And some of the dependencies can be quite complex and quite hidden. Now, when Leslie said this many years ago, this was interesting and it was insightful. Nowadays, we see this happen all the time, right? We're so used to using cloud services, and there's like this widespread outage. And if you ever see a report that's written up on it, it's always like, we misconfigured a router over, in Australia, or one of the computers went down and everything broke. So, so this is really the interesting thing. So a distributed system is this ensemble of computers. Computers are independent, right? And they're kind of loosely connected with the network. And then the key is to keep everything running, right? Make sure everything works okay. So that's kind of the challenge of the distributed system. So there is this, actually, before I get to this first question, why do we have distributed systems? Like, why do we even need them? Like, it's kind of easier to do things on one machine. So why don't we just use one machine?
Redundancy and independence in case of a failure.
Okay. All right. So we do have this independence. But why? Why don't we just build systems that work really well and efficiently on one machine?
Well, for fault tolerance.
Okay, we need fault tolerance. Yeah, right. If the machine fails, then yeah, we don't want to.
But to solve problems, you can't solve with one machine.
Yeah. Yes, exactly. Right. So those are kind of the two issues that distributed systems gives you. It gives you fault tolerance, so that if you have an outage someplace, you can keep working. And then nowadays, scale. Right. Our problems have just gotten so big that you can't work on one system anymore. There used to be this whole thing of scale up, right, where you just get bigger and bigger machines. But yeah, nowadays it's just impossible to do that. So then you run into some really basic questions that you don't have with a single machine. And the most basic of which is which machines are available, right? I mean, there's bigger questions you want to ask, like which machine is controlling the database right now, or which machine has a lock. But the most basic underlying question we have is which machine is available. Why is this question hard? Like, why is that hard? Or is this question hard? Do you believe that this is a hard question to answer? I'll tell you, most engineers do not. They do not believe this. And we're going to come back to this a couple of times because I'm sure I'm not going to convince you the first time around. But why? Why is this a hard question?
How do you define available? Is that a bit like if one machine is like connected to the network, considered available, or they have to be interacting with other machines?
Yes, that is a great question. Yeah, what does available even mean, right? I mean, is it that it's connected, or does it mean it's working well? And if it's slow, is it available? Or is there a threshold? Yeah, so you're right. I mean, even the question itself has this problem of precision. What does availability really mean? But if we can't agree on some sort of threshold, like machines respond with a certain latency, how is that hard?
Isn't it impossible? Sorry.
Yeah, it is impossible. Yeah, we'll get to that. It's just to say, yeah.
Impossibility makes it hard there. And it's because you can't tell a slow machine from a down one, right?
Yeah, that's true. Right. We have these networks we connect to, and sometimes there's delays, and sometimes things are slow. And what is even slow, right? Like we have fast processors and slow processors, and the slow processor may be going as fast as it can, but to the fast processor,
We're gonna have partitions. Slow. Partitions are bad.
Right.
Bad things can happen.
Yeah, exactly. Networks are unreliable. Partitions, are you on the good side of the partition or the bad side? How do you know, right? If you're partitioned off, right? So, you know, we have things like, you know, machines run at different speeds, we perceive time differently, packets get lost, networks get partitioned, right? CPUs get overloaded, right? Sometimes we have a fast machine and it's working and it's available. It's just overloaded, right? And it'll go away, the overload will go away. Or Java, I mean, especially when Java first came out, you know, you have JVMs and they go into stop the world garbage collection, right? Time freezes for the JVM, right? So to your Java program, like really time has frozen. And when it resumes, like nothing has happened, right? But the rest of the world, the world has moved on, right? So in short, our machines are asynchronous, right? They're independent, like has been pointed out, right? They kind of all run on their own. They run at different speeds. They have different things going on them. So we have this asynchronous behavior, and our network is unreliable, right? There's delays, there's packet losses, and that's what makes this hard, right? Now, did I convince you? Maybe not. Because, you know, a lot of times in academic papers and at the university, we say things are hard and we make it, and then, you know, the engineer is always left thinking, well, wait, okay, is this just so you can do a proof or make the homework hard for us? Or is this really a problem? Like, is it really that hard? So one thing I like to do, I'll try it out. I don't know if it's gonna work here, but, you know, usually when I give this presentation, I always ask the people that are alive to raise their hand. So if you're in this presentation and you're alive, can you click on the little Zoom button to raise your hand? All right. And then let's see, can I see that? I think I can see it. Yeah. So, right. Good. So now I look, right? So it's easy, right? I can look and I can ask this question. I usually can look and see people, but you know, most people, they haven't exposed their video, so that's okay. But I can look, and we have this raise the hand feature, so I can easily tell who's alive. And looking now, it looks like there's 6 people alive out of 20, right? So should we be worried? Like, should we call ambulances for everyone? Probably not. Hopefully not. I really do sincerely hope everybody's okay. But you know, there's reasons for not responding, right? Probably half of you can figure out how to raise your hand in Zoom. I always forget. It takes me like 5 minutes to figure out how to raise your hand. Some of you are probably watching a really interesting video on YouTube, right? So you're a little distracted right now. Oftentimes when I give this presentation to companies, the managers are all doing their email. So they never like raise their hand. But even finding availability just with people can be hard, because it's hard to know who is active, even with people, right? So oftentimes when I think of distributed systems, I think of people, and you'll notice I say this during the presentation. For me, machines are people, and I do that because it really helps me understand what's going on. If I think of machines as people, because we're all asynchronous, right? We think at different speeds at different times of the day. You all are 2 hours ahead of me. You're probably a little bit more woken up than I am, right? So we have the same problem, right? You walk into a room, you don't see everybody. People zone out that should be paying attention. So we have the same problem, all right? So even now, you can put your hands down if you want to. I'm not going to use the raise hand anymore, so it doesn't really matter if you put it down. But
That's good, because my arm was getting tired.
yeah, good. Thank you, James. Yeah. So it still seems like we should be able to do this, because we have network things. We have network building blocks like TCP, right? TCP gives us a reliable channel. Certainly, we should be able to use TCP to figure out who's alive, right, and who's around. But we have this thing, this was alluded to before. There's this really great result called FLP. FLP is, it's kind of the halting problem of distributed systems, right? In computing, we have this halting problem that says, you know, given a program, any program in general, you can't decide if it's going to halt. Some programs you can, but not all of them. There will be some that you can't decide upon. So FLP says the decision problem for a distributed system is impossible. Like, always being able to come to this decision is impossible. Now, it sets some context, right? So we need to make some assumptions before we can make a statement like that. So these are the basic assumptions of FLP. First, we have asynchronous processes, right? Our computers are asynchronous. So it's good they make that assumption because it reflects the world in which we live. They make a stronger assumption about the network than we actually have. So the networks we use today, messages can get lost, right? They're best effort networks. But FLP actually assumes messages will never get lost, right? But they may be delayed, right? And obviously messages are always delayed because we have this speed of light thing that makes it, you know, hard to get messages without delay. So, so it assumes asynchronous processes, all messages will eventually reach their destination, but they will be delayed. And then the problem we're solving, we need to agree on one bit. So in general, we want to decide on big things, like, you know, who's in control, what the configuration is, membership. But the problem they set up is just one bit, right? We just need to decide yes or no. And the failure assumption is that one of the processes can fail, just one. So usually when we're working in distributed systems, we assume that there's going to be a number of processes failing. Usually we want the majority to stay alive. Sometimes we need a super majority to keep running before things start having problems. But in FLP, they're just assuming one process failure. And they're saying, even with these simplified assumptions, I'm really sorry about the gardener, by the way, if you hit the lawnmower. But even with these simplified assumptions, we can't always decide, even on a single bit. So I did send out the paper. It is kind of complicated to read, but kind of breaks down to, actually, did anybody figure out why this is a problem? What was the basic strategy with FLP? How did they prove this? This isn't a test, so I just thought maybe somebody had a really cool insight. So the key thing about FLP is that when you start, there has to be a state that is indeterminate. They call it bivariant, right? So basically, you have the state of the system. You have all these processes, all these distributed processes, and they're going to start with some initial state. Now, in order for this to be a decision problem, you need to have the ability to reach true or false, right? There has to be some state that will lead you to true or false. Otherwise, you can come up with an algorithm that says, okay, all processes, just say true, or just say false. And then, yeah, you can come to a decision, right? It'll be true or false, but you're not really deciding anything. That's just a predetermined thing. So we want, there has to be an initial state where you can reach either true or false. The processes communicate, and they have to make a decision. And the way the proof works is they go through and they show that if you start at this initial state where either true or false is possible, right? And you have to kind of communicate and decide. That at each point in the state transitions, there is a path that will lead to another indeterminate state, right? So maybe the path is something fails. Maybe the path is a message gets delayed or a delayed message comes in. But the proof basically shows that there's always going to be a path that will take you from one undecided state to the next undecided state. So you can't always guarantee that you're going to reach a decision, right? And this was very disappointing. Like when this paper came out, there were a lot of people that were very sad, because this is easier than the problems we want to solve in practice. And it's not want to solve, it's problems that we have to solve in practice. So what FLP says is, this perfect solution, you're not going to get it. You're not going to get the perfect solution. But we have the problem and we have to solve it. So what do we do? So it turns out we can get close. FLP doesn't say that we'll never be able to make a decision. It just says that we won't always be able to make a decision, right? And so the strategy that we take when we build distributed systems is we err on the side of safety, right? So when we make a decision, we want it to be a safe decision. Everyone agrees. We never want to be in a state where we don't have agreement and act like we agree or assume that we're going to make a decision in one way or the other, right? So we want to be safe. If we reach agreement, we'll say we reached agreement. But if we haven't reached agreement, then we'll just stay in that indeterminate state. Now, we do also make a couple of things. This asynchrony, we can bound it, right? We can say, processors run faster or slower. There is delays in sending messages. But, we're going to put a bound that says, after a second, a message should have reached, or maybe 10 seconds, a message should have reached its destination. So we can put a bound on this asynchrony. Always keeping in mind that first point where we're safety first, right? If we can't decide, we just don't make a decision and we just wait. And that's kind of this last point. So what we do is in FLP, when we transition from an undecidable state to another undecidable state, we want to make those cases improbable, right? So they can happen. For all the algorithms out there for distributed systems, you can come up with a scenario in which nothing works forever, right? But we just want to make that very improbable. And if you think about it, this is the world in which we live, even on a single machine, right? There's gamma rays coming, okay, I don't know anything about physics, right? But there's gamma rays coming in that are like flipping bits in our electronics. And if they flip everything just the right way, we aren't going to notice it even when we have error correction. There's things that can happen that will cause errors that will go undetected. I mean, we live in a world of probabilities. And so distributed systems is no different. So what we really want to do is come up with algorithms that with high probability allow us to make decisions. And if we can't make a decision, we just stay in that state, and with high probability, we will transition out of that state soon, okay? So this is how we get around FLP. This is why FLP isn't the end all. But it is a good thing to keep in mind, because when you build systems and it looks like you have come up with the ultimate solution, you should really go back to some of these fundamental theorems and say, okay, it looks like I've invalidated this theorem. What am I doing that, what assumption am I making that is different? Like, is it that I do have this corner case that it is possible for me to just not decide forever? Or am I making some assumptions on synchrony or message loss that I can, or maybe I shouldn't make? So that's why these fundamental theorems are really good. And it's also why they're not the end of the world. Okay? Any questions about this so far? All right. Yeah. So probably haven't convinced everyone. There's engineers out there that will still look at this and say, dude, I have ping. I can just ping the machine and I'll know it's alive, right? I think, I think somebody mentioned something along these lines before, but this is something that happens in practice that's really exciting, actually. So you're in operations, right? You're managing a big system, and you're trying to figure out, hey, it looks like one of our machines is dead. I wonder if it's still working. So you ping it, right? So I ping 192.168.254, right? Ping is our network tool that allows us just to send a message and get a response. And if we get the response, we know it's working. So you ping the machine and it comes back alive. You're like, yay, the machine's working. You SSH into the machine. SSH fails. What? Is it alive? Do we count this? Like, what's going on? So this actually happens in practice. I should say it happens often, but in aggregate, it happens all the time, right? And we got to make a decision here about the health of this machine and its availability. And it also means that if our membership algorithm was based purely on pings, we're going to get the wrong view of the system sometimes when we have network connectivity, but our systems aren't actually working. All right. So we can use TCP. So I wanted to talk a little bit about some of the TCP fallacies I've seen in practice. So TCP is this awesome protocol that we build a lot of wonderful applications on. And one of the reasons it's so awesome is it takes this unreliable network that we run on and it gives us a reliable stream, right? TCP, guaranteed delivery. That's the whole mantra of TCP. It's really awesome. So certainly we can, it has guarantee in the name, right? Certainly we can do something that's guaranteed to work with TCP. So I've seen code like this often for failure detection. You'll have two machines and then they want to know if each other is active. And so what they'll do, one machine will open a TCP request to the other machine, right? So now you have this TCP connection, this guaranteed channel of transmission between these two machines. And then the machines will just simply try and read from each other, right? They'll do this read call. And if the other side fails, the read will return an error, right? And then what will happen inevitably is one of the engineers will look at this and say, wait a second, are you sure this works? Does the read really return an error? And they'll say, okay, let's test it. We're engineers, we'll test it, right? So, so you write this code and you run it and you start it up on the two machines. And now both processes are doing this read, right? And then you Control C, or you kill one of the processes. What happens to the read on the other process? Has anybody done this before? What will this read return, or will it return? Right. So it turns out the read will return an error, right? It'll be sitting there waiting. When you kill the other process, the other side, the read will return and it'll say connection closed, right? And then the engineers will look and say, this works. We know how to tell if the other side is alive. We just do a read here. Now, the question is, why did it work? Does anybody know why it worked?
I guess I have a quick question about the connection close thing. Is that the same thing we would expect? Otherwise, I guess from my experience, I'm used to connecting to databases, and if you lose that connection, it'll explicitly say like, "Hey, we lost the connection." Is that
yeah, exactly? It's very similar. A similar thing happens when you do databases as well. So the question is why? Because basically you had and most, I can't say all because I don't know a lot of them, but most database network connections are built on TCP as well, right? Which is why you get similar behavior. But usually what will happen is you know, you do a connect, right? Right? And then, you know, you do the three-way handshake, but eventually you have this connection going, right? So there's this handshake that goes back and forth, right? And now each side does a read, right? You do a read here, you do a read here on this connection, right? So what happens when you stop this process, or you stop the database process, for example, this process really isn't running just like on its own. It's running in an operating system, right? So one of the nice things that an operating system does for us when we stop a process is it cleans up everything, right? So when you push Control C or you killed this process, you closed the connection. So there's a little bin packet that goes out saying to the other side, hey, you know that socket that you guys have going, it's gone now, right? And that's why the read returns, right? That's why the read returns with an error, because the other machine sent a packet back saying it's done. That's why your test worked, right? If the two engineers, when they ran that test, that's why it worked. Now, unfortunately, not all failures work like that. And there's actually a way to test it. There's a better test that the engineers could have run. So on Linux or on Unix, you can do a Control Z or a suspend signal, right? And what this does is it takes the process and it says, suspend. Just don't do anything anymore. It's not killed, it's just suspended, right? Now, if you suspend the process, this fin isn't gonna go out, right? So the read will just sit there. It'll just sit there waiting. And of course, nothing will happen because the process isn't technically dead, it's just suspended, right? So if they did that test, but then they can argue, okay, but it's just suspended, it's not really dead, so is it really a failure? It gets back to, you know, is it really alive or available? So there's another test you could do, right? You know, there's a cable going from here to a switch, right? I'm not an artist. I can't draw a cable, but let's assume that this is the cable, right? So you can cut the cable, right? You can pull the cable out of the switch, right? So you've effectively partitioned the operating system from the machine. So what's gonna happen now? No fin. There's not gonna be a fin. That read will sit there and wait forever. If you're really lucky, maybe a switch might send something, but probably not. So this read is going to sit there saying, oh, I'm so glad the other side's alive. But really, everything's gone. It's just you never got the signal from the operating system that the other side had died. In the early, I think it's like the 80s or the 90s, there was a lot of work in distributed systems of, you know, this last gasp of signals, right? So the idea was we would build machines that just before they would die, they would send out a signal telling everyone, hey, I'm going away, right? And that would help us solve a lot of problems if that worked. It doesn't really work very well. We can't count on this, right? We can't count on this. So how do we solve this, right? Because this is kind of a bummer, but you know, TCP, it has guarantees, so we should be able to solve it, right? So it turns out there's this really cool thing in TCP called keepalive. Has anybody heard of TCP keepalives? Yeah, right? What do TCP keepalives do?
Keep the connection open.
Yeah, it keeps the connection alive, right? In the background, if no traffic is going on, it will just send a little keep alive packet, just kind of under the covers, unbeknownst to you. And if we had used keep alive, what would happen is there would be this keep alive processing going under the covers. And if that machine disconnected, this keep alive packet would go out, it wouldn't get responded to. And then the operating system on the machine running, you know, that was still working would detect, oh, that connection, I'm not getting responses to my keep alive messages, it's gone. So I will close it. And then the read will work. and everything will be awesome. So it looks like Keep Alive might be the answer. But let's look a little bit more closely at Keep Alive. So there's these things, these standards called RFCs, right? They're written by the body called IETF, Internet Engineering Task Force. They write all the standards that our TCP is based on. So there's an RFC that talks about Keep Alives. Now, one of the things that's really interesting about reading internet standards is they capitalize certain words that look a little bit crazy when you first see it, but may and must, you'll notice, are capitalized. That they have specific meanings, right? When in the IETF, when you write standards, if you say may, that means you may or may not implement this behavior and still comply with the specification. Must means you have to implement it. Like if you don't do it this way, you are out of compliance with the specification, right? So this is the RFC that talks about Keep Alive. So it says implementers may include Keep Alives in their TCP implementations, although it's not universally accepted. So that functionality might not be there. Now, good news, most modern implementations of TCP have Keep Alive. So that's cool. All right, so let's keep reading. All right, so if Keep Alives are included, the application must be able to turn them on or off. Seems reasonable. But they must default to off. So if you want to use Keep Alives, you have to turn them on, right? Because they're not going to be turned on by default. Keep Alives must only be sent when no data or acknowledgement packets have been received. That's cool. That's what they're for, to detect this idle time. So there's this interval in which we send these Keep Alives. This interval must be configurable and must default to no less than 2 hours. So by default, if you start using Keep Alives, you'll find out that the other side has gone away in 2 hours, right? So the responsive distributed system we want, right? So you can crank it down. And the defaults I looked on my Linux system, it corresponds to 2 hours basically. So yeah, so if you want to use Keep Alives, we need to crank it down. But there is this bigger question about whether or not TCP is really giving us what we really want. So we do have this idea that, again, because it's a guaranteed channel, that if we send data over TCP, that it's getting there, right? That's not really the guarantee that TCP is providing. And let's look a little bit more closely. So let's say we have these two processes and they're sending data. And this first process here, the one on the left, it wants to know when the data has been processed, okay? So it does a send, it does a TCP send, it sends 99 bytes of data over to this process on the right, right? And the question is, when the send returns successfully, has the data been processed on the right? Okay. Now, the answer is no, right? Because send returns when the data has been sent. We don't know. I mean, like this process on the right, it could receive the data and then, context switch, something else is happening on the system. There could be a substantial delay before it actually processes the data, and processing the data can take a while. So yeah, clearly we're not going to know when the data has been processed just from TCP, and that's okay. But what about delivered? If we get the RC99, do we know that it has been delivered to the other side? Like this other process, has it at least received the data? Turns out the answer is no, right? When send returns successfully, what is the one thing we know? We actually only know one thing for sure. Does anybody know?
It's out the door.
It's what?
It's on the wire.
Oh, it's on the wire? Okay.
Yeah.
That would be cool if we knew that. Not quite. We actually don't know it's on the wire yet. What do we know? What happens before it goes on the wire?
It goes down the network stack.
Yeah, exactly. It goes down the network stack into the kernel. So when send returns, we know that the data has made it to our kernel. Like, we don't even know it's gone out the network card yet. It may never go out the network card. Send can return successfully, and it may never leave our machine, right? So that's kind of disappointing because, you know, TCP has this really cool acknowledgement thing here. What if we could like hook into TCP and we could get this acknowledgement that came back, right? Would that give us a better idea of what was going on? Turns out even with that, we don't know. So when our kernel gets an acknowledgement, what does that mean? Does it mean the receive has been completed? That's what we'd like. It'd be kind of cool if the acknowledgement means the receive has been completed. It actually does not mean that. Acknowledgement means it's in this kernel on the other side. The application may never receive it, right? If the application terminates, it may never get the data, even though we acknowledge the receipt from the other side. So I point this out simply because these are some of the problems I've seen, some of the assumptions I've seen in distributed systems that get built based on TCP that are invalid, right? And they work extremely well, like through test cases and initial production. But then what happens is you get these systems deployed and you get these weird behaviors every once in a while. And it's really hard to figure out. And it's because if you make the assumption that a send that completes successfully means it's been processed on the other side, often you'll be correct. Your assumption will be correct, especially in the space-time continuum in which you can't really tell exactly when things happen, you know, in the world in which we live. So it really looks like the send, when it returns successfully, it's been processed on the other side successfully. You can do measurements and it really looks like that, but it's not happening. And life will teach you that in some corner cases that will happen in production that will be really hard to figure out. Okay, so again, this is not to disparage TCP. I love TCP, it's my favorite protocol, right? But you gotta be careful, you gotta watch out for it. It doesn't give you the guarantees that you really need. There's this other fallacy that I love because it's so logical, right? It's the I process, therefore I am fallacy, right? So you're writing your code, you're coding out, and your program's running. Again, I like thinking of them as people, right? So here's your code, you know, your program's running, it's going along, and of course it's alive. Like, if someone were to ask your program, are you alive? Of course I'm alive. Look, I'm at address, you know, 7F327, getting ready to execute this move instruction. Of course I'm alive. But is that true? And I think one of the things that happens is when you try and do a connect, right? So you're a distributed process, you try and connect to another distributed process. Fails. All right. So now the logical thing is, if I can't connect to someone else and I'm alive, that other process must be dead, right? It's logical from that process's point of view, you know. In the political environment today, this is often what happens. I'm obviously right, and I disagree with you, so you're obviously wrong, right? So yeah, so this is something we can't do in distributed systems today, right? So often, what happens is we get in this situation where, you know, processes can't communicate with each other, but we need to make progress. So we have to figure out, we have to decide, those processes over there, we can't talk to them. We're going to assume that they're no longer running, right? We're going to make that assumption so that our system can move on and we can keep going. Now, those processes might still actually be running. It's just that nobody knows it except those processes. And when those processes come back into the system, they need to realize that they don't exist anymore, right? And make sure that that stays true, right? They can't come back. So we can look at this. We can look at this problem of coming back. And it also brings up another fallacy in distributed systems. When we work on operating systems, we studied mutual exclusion, right? It's one of the things we study in the operating systems class. So we grab a lock, and we grab a lock to make sure that you have exclusive access to a resource, right? Maybe it's a piece of memory, maybe it's a counter, maybe it's a database, whatever, right? But operating systems, we know we grab a lock, we have this exclusive resource. Now we have problems we need to avoid, like deadlocks and everything, but we do know if we grab a lock, we're the only one that can access it, right? We need to do this in distributed systems as well, right? Like for example, in this example, we have a leader process, right? So we have one process that we want to be a manager, and it needs to manage the rest of the system, right? It needs to make sure systems are rebooted for maintenance, it needs to control who's the database master, various things that this leader process is going to do. So to do this, it acquires a lock. And holding this lock, this is the leadership lock, it can guarantee that no one else will take leadership action, right? That way it can safely reorganize the system and not worry about conflicting commands, right? Now, of course, we also need to tolerate leaders failing. So if a leader fails, then eventually we're going to reclaim that lock so that another leader can take the lock and work. So if we just use locks the same way that we use them in operating systems, we have a problem. And the root of this problem is in an operating system on a machine, when there's a catastrophic failure in which a process is lost track of, it means the operating system has crashed. So basically everything stops. So if there's a failure in an operating system that would affect the validity of locks, there's a failure in everything, and everything just stops, right? Distributed systems, no, we're asynchronous, like we're independent people, right? Or processes, right? So they're running, and a failure of one will not affect the others, which is good for fault tolerance, but bad for other things. So let's look at this scenario. Leader acquires a lock, and then the leader prepares to send a reboot message to server 27 and wants to reboot server 27. So the message already prepared is ready to go out through the TCP send call. But just before it does it, the leader server hangs. Maybe the CPU is overloaded. Maybe there's the stop the world garbage collection. For whatever reason, it hangs. These hangs can take a long time. I've seen in the early days, there were garbage collections that would take tens of minutes, right? That's a long time. And then, when garbage collection is finished, the process resumes as if no time had passed, right? So anyway, this leader gets overloaded, and so its lock times out, right? So to the rest of the world, it's considered crashed. So we need to run. A new leader grabs the lock, and then the new leader looks at the world and decides, okay, I need to do maintenance, and maybe it decides, okay, server 27, yeah, it does need maintenance, but right now I really need it to be the DB master. So it tells server 27, you're the DB master. So it starts doing DB master stuff. Now, after that, this old leader, the overload starts getting resolved, and finally the thread that's going to send that message gets scheduled, right? The thread's like, yay, I can finally do my job, and it sends out the message to reboot to server 27. Server 27 reboots. Now everyone's scrambling. What's going on? Why was server 27 rebooted? Well, obviously it's a lock server. Like, obviously, this lock server did not provide exclusive access. But was it the lock server? Should they be blamed? They will be blamed, by the way. I will tell you that right off the bat. But should they be? Is there a better way we could have done this? So it turns out there is. There's a fence. There's a concept called fence in distributed systems. And the idea of a fence is you have this token that will basically invalidate everything that came before you, right? So it'll fence everyone else off, okay? So we tweak this slightly, this scenario slightly. So the first leader takes a lock. And when it gets this lock, it gets a monotonic value that represents the lock. Let's say the value is 102. And it prepares to send a message to server 27. Now, all the messages are going to include this fence, this 102. And now, again, server hangs. So the scenario is exactly the same. New leader gets a lock. It has a new fence value. It's going to be higher than the previous one. Tells server 27, you're the master, right? Server 27 says, oh, okay, yeah, this fence is higher than I've seen before, so I'll be the master, right? And now, again, the overload goes away a little bit on the old server, and this reboot message goes out. And now, server 27 gets this reboot message and says, oh, this is old. This is from an old fence. I'm just going to ignore it, right? System saved. Everything's good. We just averted, you know, a destructive event, but no one knows because it just works, right? And the poor developer that did all the fencing work gets no glory. Actually, what the poor developer gets is, why are you passing around this fence value? This just makes everything more complicated. Why is this here, right? So, so there are really great solutions out there. It does make things a little bit more complicated. And to people that aren't familiar with the problem, you really need to document it so that they understand it. So they don't say, okay, I'm just gonna send all my messages out with a fence value of max n, because I found that they all go through that way, right? Then we're back to the original problem. So I wanted to, there's actually a whole list of distributed computing fallacies. So these are the classic ones that they seem so obvious, but when programmers write to them, write their code, oftentimes they don't keep these in mind. Fortunately, you know, the networks today, they are really reliable. I mean, look, we're doing Zoom. Like, we're not even getting jitter. Well, okay, I'm not getting jitter. It's kind of cool, right? I mean, it's going over the internet, the best effort. They're doing really good effort, right? This is really awesome. The cool thing about video conferencing I really love is that we all recognize latency isn't zero, right? When you've been on the video calls and people start talking over each other because there's just this very imperceptible delay until you actually try to talk to each other. So it helps us recognize that latency isn't zero, which is really great. But these are all really cool. I did want to illustrate one. This is number 6. There's one administrator. Does anybody know what on-call is? Do you guys have on-call?
Yep.
Oh, what is on-call?
Basically, something happens and it gets paged out for someone to fix something.
Right, exactly. Yeah, so on-call is a very familiar term here in the Valley. We all do it. It's part of DevOps, which is big, right? So the idea is that you write code, you're in charge of it. If something breaks, you need to fix it, right? And that includes if it's after hours, because, you know, most things are 24/7 now. So you have on-call. And so what happens is you'll be at home, Christmas Eve. This happened to me, 11 o'clock. A system will break and you get paged on Christmas Eve, right? And working, trying to get the system back up. Now, oftentimes with the on-call, what will happen? Somebody will leave their phone off or their phone will die. So you'll need to call a backup, right? There's usually a backup to on-call. But sometimes what will happen is the backup will get called and the primary will figure out that they got called and they'll both start working on it, unbeknownst to each other, because after all, it is 11 o'clock on Christmas Eve, right? And they can start doing things, it's like the 2-liter scenario. They can start rebooting different machines and causing even more damage because there's 2 administrators. So I wanted to bring up one other case, or fallacy. Homogeneous machines have homogeneous performance. So yeah, you know, we have different versions of machines and different iterations, but you do expect if you buy a batch of machines at exactly the same time from the same place, same manufacturer, and everything looks exactly the same inside, that they'll have the same performance. It doesn't happen. It doesn't happen. Sometimes the machine will get a runaway process or have an update going on, but I saw this really cool thing in practice. We had some servers that could write 50% faster than other servers in production. And I looked at it, and they were exactly the same servers. It was driving me crazy trying to figure out how in the world they had different, and it was consistent. So I got other people, we were all digging into it. We figured out that even though all the hardware was exactly the same, the disk drive on the faster servers had a slight revision of the firmware. And that slight revision made them run way faster. Maybe it was running way faster because there was a bug. I don't know, but they ran way faster. So you can't even make this. We really live in an asynchronous world, and we've got to accept that. You know, I'm totally out of time. So I just want to, I guess, leave you with Zookeeper. This motivation for Zookeeper. This is all to motivate this project I worked in called Apache Zookeeper. And it's really to solve this problem. When Zookeeper started, our systems were getting bigger. They weren't as big as they are now. I mean, now we have distributed systems with thousands, tens of thousands of machines. It's common, right? Back then, we were kind of aiming for dozens or hundreds, right? But even then, it was really hard. And so we needed to solve this coordination problem, be able to answer questions: who's the leader? What processes are out there? Who's alive? And so we're looking at different designs. Even today, there's different ways of designing these systems. One is with a library, and one is with an external coordination system. And we went, the library is really nice. Engineers love to not have dependencies on their code. So they use libraries, and that way they only depend on their own processes. They don't depend on anything else. Makes deployment easier. The problem with that is these libraries, the coordination code lifetime is tied with the applications that they're actually managing. So we went with the version on the left, this coordination service. So we have this service called Zookeeper. It's replicated for fault tolerance itself, right? It's fault tolerance all the way down, right? So we have this replicated system that clients use. So the clients will be your distributed system that you're building. And they'll connect to Zookeeper and use it to figure out who's out there, answer all the hard questions that we need to ask. And the Zookeeper service will answer them. Or, as I mentioned with the FLP, it will say, I don't know right now. You'll have to wait, right? And this allows our distributed system application developers to build these awesome applications and focus on the application logic rather than all the problems of distributed systems. So that's what the Zookeeper coordination service is. You know, there's a lot that goes into that. I guess I'll leave you with this one thing. And that's, how do things fail? This was a really interesting observation we made at Yahoo. When we, as researchers, when we design these fault-tolerant systems, we come up with all these complicated, interesting protocols to tolerate faults. And usually, the faults we're tolerating are like machine failures or network failures, right? But we looked at what happens in practice. The number one problem we found was configuration problems. They would be set up, like the different replicas would be set up with different lists of peers. Or clients would be set up to talk to servers, but half the servers were in one ensemble and half were in the other. The very definition of split brain. So these configuration problems were the most common problems we ran into, which is really tragic because in all the distributed system or the fault-tolerant algorithms that we use, the base assumption is that we have a correct configuration. So it was really a tragic finding. So that we still have a lot of work to do. But I see that I'm completely out of time. So I do appreciate your attention, and I'm happy to take any questions if you have any.
Sure. So I have some fun stories with Zookeeper. So we use it at the startup I'm working at, and one problem that we experienced is that it's been running fine, pretty well. We have a 3-node setup, and and at one point the leader node dies, and so it fails over to another node that is available. But it turns out that the available node, well, it's available by every metric. It's actually, it was a different instance size, and so it's actually not powerful enough to keep up with and so it was effectively down because yeah, the latency
Yeah.
was too high that it just crashed our entire system.
Yeah, that is a problem. Yeah, it's really, this gets back to what does available mean, right? Just because it can respond to simple packets doesn't mean that it can tolerate the load that you're going to throw at it. So yeah, that is a problem. Did you try moving to like a 5 server ensemble to make it better?
So I think we just ended up upgrading that one instance.
Oh, okay. Yeah, that works too. Yeah, good. That works too. Yeah, that is one problem with Zookeeper. One thing that would be really awesome to do is that Zookeeper has an assumption right now that any node is a potential leader. It would be really cool if you could say, look, we have this preference. We'd really like that node to be the leader because it's the most powerful, and then maybe this one, because that would be really awesome. But there isn't that functionality in there.
I have a question.
Sure.
Yeah, so about the Zookeeper diagram you show, so each user is, can you go back to that?
Yeah.
Oh, this one, yeah. So each client is connected to the server, and you mentioned they ask questions, and the Zookeeper like set a probability threshold. So if the probability threshold is not met, they wait for this, for the like optimal probabilities. So how do you quantify that probability?
Yeah. So it turns out there isn't a probability, actually. That we implicitly minimize things with a probability. So actually with Zookeeper, the probability comes in actually 1 point. When Zookeeper, when these servers are coming up, they need to elect a leader, right? This is the server among servers that is going to control all the modifications to the system, right? So we have this leader election algorithm. It's a decision problem that we have to make. Now FLP says we can't guarantee that we'll always make that, right? And so we have a leader election algorithm that with high probability elects one leader, right? So, and the probability is both that a leader will emerge and that only one leader will emerge. Both cases are possible where no leaders emerge or 2 leaders emerge, right? And so what we do in Zookeeper is if 2 leaders emerge, we catch that case and we start leader election again. And if 0 leaders emerge, we just keep doing leader election. So this is the case where, and it's improbable, right? Generally it doesn't happen, but if the probabilities work out and 2 leaders emerge or no leaders emerge, we're just going to try again and hope that the probabilities work out better in our favor next time, right? And if the probability is low, then we will be able to succeed next time.
Okay. Yeah, thank you.
All right.
All right, I may be talking a bit through my head here, but you mentioned quite a few times that TCP is your favorite protocol of all time. As you know, HTTP 3 won't be using TCP. What are your thoughts?
Yeah. Well, okay, to be honest, it won't be using TCP, but it does use the basic underlying mechanisms. Like it replicates a lot of TCP under the covers, right? It just does it slightly differently and more efficiently for HTTP, right? So it can support like multiple channels, for example, multiple conversations through a single virtual connection. So they build it on UDP, but it's almost a re-implementation of TCP. So yeah, I like it.
Yeah.
I like both of them. They're very cool. I think the one problem I have with HTTP 3 that I think is a little bit disappointing is they basically replicate the important functionality of TCP again, right? And then tweak it to fit HTTP better. But the sad part about it is at least until routers and the network infrastructure gets accustomed to it, it's going to be a little bit invisible and a little confusing. So one of the cool things right now is when routers and switches see TCP, well, and firewalls, for example, they see TCP, they know how to handle it. Like, okay, I know exactly how to handle this. And then when they see UDP, they say, okay, I know some hacks that work with UDP, right? But I think it's going to take a while before all our networking equipment is going to be able to look and say, oh, okay, this is the new HTTP protocol. I haven't seen this before, but I know how to do it, right? So.
Do you think it will help in your study, in your checking that things are still online?
No, I don't actually. No, I think as far as like detecting faults, you still have the same basic problem.
Okay.
I mean, but it's still a great building block. I mean, TCP is a great building block. You just need to add a little bit on top of it, right? You basically just need to do application layer acknowledgements as well in both cases.
Thank you.
Yeah, can I ask a question?
Sure.
Yeah, so underneath the hood, Zookeeper solves fault-tolerant consensus using a Paxos-like approach. Now, Paxos is notoriously difficult to understand. How did the developers, the engineers, deal with that?
Yeah, so I actually love Paxos. I love the original Paxos paper, the one that's like 32.
Yeah.
It has such a great background story. I just love it. And it fits my model of the world. However, it's actually not really Paxos. It's like Paxos in that it solves consensus. There's another more recent protocol that is like what we do.
Raft?
Raft, yes, exactly, Raft. So both Raft and Zookeeper's protocol is similar to a really early protocol called view stamp replication, right?
Yeah, that was, I forgot her name.
Yeah, I have too, yes. I want to
She
say
won a Turing Award, so.
Yeah, but the problem with that first paper is it was impossible to read. It just it was really hard to figure out what they were doing. So I think that really blunted the impact of that first paper. But I think that the cool thing about Paxos, I love Paxos, and I love the way it presents the problem and solves the problem. But from there's very significant engineering differences, which I think is what you're alluding to.
Yeah.
Because one of the problems, I guess the nice thing about Paxos is it focuses on solving consensus for one value, right? And it really is like laser focused on that. And it does it with a protocol that you can kind of understand, like it makes sense conceptually. Implementing it is hard, right? And the problem is that you have to take that protocol and make it work with multiple, because we're going to want to decide on millions of things, not just one, right? So you need to take it to multi-Paxos. So you're actually doing multiple decisions. So that makes it complicated there. And the other thing too is Paxos stops when the decision is evident, not when everyone knows about it, right? So it gets to a point where the value, there is now a known value. This is the value that will emerge, but it doesn't get you to the point where everyone else knows the value, right? That's left as an exercise to the engineer. And that's a hard exercise. It's hard to do. So in ZAB and view stamp replication and Raft, one of the nice things is it kind of works it all the way out for you. Like it really gets you to the point where everyone actually learns the value. So yeah, so I really like Paxos. And I do think there is a lot of, I guess one thing I've noticed is for big Paxos, not for big, I'm generalizing now, but for many Paxos aficionados, right? They really see the world as everything in the world maps to Paxos. Like all consensus algorithms come back to Paxos. And I think that's a wrong view. I mean, yeah, academically, like theoretically, at the core of it, there is all of the protocols have this moment in time when the decision value is reached. And that moment in time is reached in a very similar way in all of them. But then all the rest of the mechanisms are different, and it's richly different. And I think it's great to have those choices, right? Because for everything else we have choices, right? We have a bunch of different kinds of databases, and they all, at their core, implement a relational database, right? But they all have their variants, right? And then there's the NoSQL, which a lot of databases people complain is actually just a database, right? But you know, it's useful to call them something different. Although NoSQL is kind of antagonistic, but yeah. So I think yeah, I agree with you that Paxos is hard to implement, and actually I think that the key problematic thing from an engineering point of view with Paxos is having multiple outstanding requests at a time. So performance, for performance, you really want to have like a lot of requests going through this pipeline, right? And with Paxos, if you have more than one request going at a time, you can get into weird, I shouldn't say requests, instances. You can get into some weird situations in recovery where you get failures, and then you get this strange mix of decided values. But I think all of these protocols have really great applications and also really great instructional value.
Right. Yeah. Thanks. Yeah.
All right.
More questions?
Cool.
So Ben, actually, I have one last question. Which
Sure.
you mentioned about the ACK sort of, in the TCP.
Yeah.
That this ACK could be used, but I never sort of heard back that how do you actually use those ACKs? Like they are meaningful, right?
Yeah.
From
Yeah,
your presentation that those ACKs are not meaningful.
No, I didn't mean to imply that. What I was trying to point out in this slide is the ACKs are extremely meaningful for the TCP protocol. Like the ACKs is what allows TCP to do its guaranteed delivery and to get everything, but and even more than that, like TCP uses it for like rate control and everything else. But I think that the thing that it doesn't, that ACKs don't give you, is some application level information that you really think you could get that you can't. So like at the application level, an ACK isn't very meaningful to you, right? To the application. Right. The TCP, of course, and it's what makes it work. But as an application, the fact that the other side acknowledged the receipt of these bytes, it doesn't really mean much to me. And if I really understood what the ACK meant, I'll realize it really doesn't mean anything to me at all, right? So that's what I was trying to point out. From the application's point of view, even if the application could see the ACK, it doesn't have meaning, because that ACK really it has great meaning and great utility for the TCP protocol. Okay. But we build layers and networks in layers, and sometimes we can cut through and like get information for a higher layer from a lower layer. Right. But in this instance, even cutting through, the ACK isn't going to provide much to the upper layer. I see. Well, yeah, that was my question. It was great talking to you. Oh, go ahead.
So something in my job, we've tried setting up several. We use AWS, and so we have CloudWatch to try to monitor the various metrics on our instance hosts. They're kind of like a framework or best practice for, like, I guess the way we decide if a node is available is like we track all the things like what's its memory usage, is it disk full, like what's its response rate, all those things. Is there like kind of a formal or formal way of doing that?
Actually, when you do that, there's also this implicit other thing that's going on. So actually, it's really good you do that. because it gives you, it really is a health check. So when you ask, is it available? You actually have data. You can say, well, I really think it is available because there's disk space, there's plenty of memory, the CPU isn't overloaded. So you can make a very informed decision. And the other thing that is happening too is this data is being collected, right? It's either being pulled or it's being pushed. So you actually have a recent acknowledgement, right? So technically your answer is, well, I know that 1 minute ago when we got our statistics back, it was available. So I think it's pretty safe assumption that that it's available now. We'll find out in 1 minute if that assumption was valid, right? But yeah. What was that?
Well, that's another thing. You actually try to use the service for what you're going to do.
Yeah, that's true. Yeah, you can try and use the service as well. Yeah, that's true. That's true. Yeah, usually what happens, actually, it's funny, and it gets back to Leslie's quote about, I can't use my computer because a computer I've never heard of failed. It really gets, these systems are so complex. That's why, you know, oftentimes when we work on fault tolerance, we're really focused on one component. But if we look at how that component is deployed, like there's some really great architecture diagrams. I wish I would have, they're all proprietary, but I would love to be able to use in a presentation, because you look at this fault tolerant component you're talking about, and then you say, okay, but this component is really used by this other system, and you zoom out. You see that this whole complex system is built around it. And then you say, you know, but this system, this is really a core component of this other system. You zoom out, right? And usually these systems we use today, they're just stacks and like this graph of like interlocking systems. Like when you go to Facebook and you go to Google and you look at that one page, like there were 100 computers that just worked really hard for a couple of milliseconds to produce that one page for you, you know? And so it's really interesting to see how complex the interaction is. So sometimes what happens is you go and you get that one page and it's like, it didn't work. And then you're like, I wonder why. And then the visibility information, the data you're collecting becomes very valuable. Because it's like, okay, 1 minute ago, this service was unavailable, but why? Well, and then you look at your dependency graph and then you realize, oh, look, you know, way down deep in the stack, that server over there ran out of disk space. And it turns out, since it's a replicated server, they all ran out of disk space at the same time, right? So, yeah, so it's great. Those metrics are great for both figuring out if in the near future you're healthy, or figuring out what went wrong in the past. Okay, great being in Chicago again.
Actually, funny enough, I'm actually in Santa Clara, so I'm in your neck of the woods.
Oh, nice. Oh, very cool. Oh, that's why you have that background picture. It really does look like. Yeah, it's pretty terrible. It's so depressing outside. It's so sad.
It is. Yeah.
Cool. Well, it's great seeing you all. And thanks again, Tanya. And you're muted.
Thank you so much. This was fantastic. We learned a lot of fallacies. And hopefully, we'll not make those. I think we should be writing a book of.
Oh, you know, there are plenty of books on fallacies.
Okay.
Actually, that list is, I got it from the internet. It's not even my list. So.
Okay.
Great.
Okay, great.
All right. Thank you.
We'll need your slides, Ben. So please.
I will send them to you.
Okay. Thank you.
All right. Thanks, Tanya.
Thanks everyone.
Bye,
Thanks everyone for coming. Bye-bye.